A cable is very flexible compared to other forms of structure. Therefore, shear force and bending moment do not develop in cable since its stiffness in transverse direction is zero. On the other hand, loadings applied on cable are converted to tension that acts longitudinally along the cable profile. Cable is assumed inextensible, where the geometry of cable before and after loaded should be the same. This assumption simplifies the analysis of cable. Moreover, the self-weight of cable is usually considered negligible. The most notable examples of structure with cable are cable stay bridge and suspension bridge. Let's check out this simple cable problem. The span of cable is 20 meters and the sag is 1.5 meters. The cable is subjected to 5 kN per meter of uniformly distributed load. Assuming the cable has a parabolic shape, we can determine the curve function by using this equation. The lowest point of the cable, C, is located at 10 meter ordinate. We can determine the curve function by using only half of the span, where the lowest point is met origin. Now, we have a parabola with a span of 10 meter and elevation of 1.5 meter. By substituting these values into the general equation, we obtain the curve function. Note that the value of x should be measured from point C. First, let's determine the support reaction. This is straightforward since the structure is symmetrical. As a result, the reaction AY and BY are both 50 kN. From the curved parabolic function, we can determine the general equation of tangent slope at any point on the cable by determining the first derivative. The inclination angle of tangent can be determined based on this derivative by involving an arctangent function. In cable, the horizontal component remains constant at any point. This can be derived from a series of steps. However, we are not going to show it in this video. This component can be determined based on the loading and geometry of cable. For this example, the constant horizontal component is 166.7 kN. The limit of x is from 0 to 10 meter, measured from point C to supported end in either direction. In other words, we can simplify the problem by analyzing any half of the cable. Then, let's cut the cable and expose the axial force developed in cable section. Along x direction, we have our constant force component, and along y direction, we have the exerted force. Using force polygon, the tension in cable due to these mutually orthogonal forces can be determined using one simple formula. From the formula, we know the tension in cable is a minimum when x is 0, which is also the lowest point on cable. Let's say we want to determine the tension in cable for every 1 meter interval. From calculation, the tension in cable increases with ordinate x. Maximum tension occurs at the support. Since the cable is symmetrical, by mirroring the result for the right half, we get to see the whole picture of the internal force developed in the cable. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.